We shall today discuss some more problems on integration by parts. What I'm going to call this method as I method. For example, let's say I want to integrate sec cube x. We always feel that this is a substitution method problem, but this is not a substitution method problem. It's integration by parts. First, what we need to do is sec cube x should be splitted as sec square x into sec x. Now, we need to decide which is the first function and which is the second function. Now, out of these two, integral of sec square x is, you can do it easily. You have a direct formula for integral of sec square x. So, our formula is first into integral of second minus integral of derivative of first into integral of second. So, the second should be integrable. Out of the two, sec square x is the direct integrable. Hence, what I do is take this as second function and this as a first function. When you apply the formula, first into integral of second minus integral of derivative of first into integral of second whole into dx. That became sec x into tan x minus integral of sec x into tan x. Again, integral of sec square x will become tan x into dx. That is, integral of sec square x is replaced by tan x. Derivative of sec x is replaced by sec x into tan x. Integral of sec square x, one more tan x will come. Now, that's all we do with integration here, integration by parts. Now, I said this is I method. I method means bring the question back to I. So, what I need to do is, I need to bring an integral sec cube x in this function. So, this sec x into tan square x can be written as sec square x minus 1. So, what I've done is, I replaced tan square x by sec square x minus 1. So that I come back to sec cube x, which is my integral back to my question. So this became sec x into tan x minus integral sec cube x dx. When you open this bracket, minus sec x and minus will become plus integral sec x dx and okay, dx. Now, last step I'm writing sec x into tan x minus I. What is I? The question itself. This is I. So integral sec cube x is I. So I replace this by I. And integral of sec x is log sec x plus tan x. Now I have completed all the integration here. So I'll put the integral constant as C1. So why we put C1, you will come to know after some time. Now my aim is to find out what is I. Remember, my aim is to find out what is I. So my left hand side is I. There's also an I here. So bring them to one side. 2I is equal to sec x into tan x plus log of modulus sec x plus tan x plus C1. So I can say I is 1 by 2. I'm going to divide this by 2. 1 by 2 into sec x tan x plus log of modulus sec x plus tan x plus C, where C is nothing but C1 by 2. When I divided by 2, the C1 became C1 by 2, so that I end up in C. Usually our habit of writing the integral constant is always by letter C. So here there was one constant, but when I divided by 2, this constant changed to a new constant. That new constant is denoted by C. 2-3 things to remember in this type of problem. First thing is, we always feel like if I want to integrate sec square x, we think that, okay, I'll do substitution method, something like that. Then put tan x as t, sec square x as dx dt. Those methods won't apply here. You cannot apply by this method. So first point to remember, it is not a substitution problem. It is a integration by parts problem. Second point to remember is it is I method. Did you notice what is I method? You started from I, bring back I to the question in the integral and make I as a subject and find the value of I. This type of questions I'm going to call it as I method. This is the first question in I method. Now I'm going to teach you the next question in I method. Okay, it is similar to this only. So let's turn to the next page. So here I am going to integrate cosec cube, some number I'm going to put as 2x. Cosec cube 2x. So the method remains the same. Only thing I put a coefficient for x so that you understand that the same idea is applied here. So it is split. It's going to be split as cosec square 2x into cosec x, cosec 2x. Out of this 2, which can be easily integrated, cosec square can be easily integrated. And if cosec square can be easily integrated, that should be the second function, because always second function should be integrable. So what I do, I take this as second function and this as the first function. So our LIAT rule doesn't apply here. Then first function is cosec 2x into integral of cosec square 2x minus integral of derivative of cosec 2x, first function into integral of second, integral of derivative of first into integral of second, whole into dx. This whole into dx is very important. So that became cosec 2x into minus cot 2x by 2. Because when you are integrating cosec square 2x, you need to divide by 2, minus derivative of cosec 2x minus cosec 2x cot 2x into 2. When you differentiate cosec 2x, derivative of the angle part, into minus cot 2x by 2 into dx. In integration, the coefficient of x is divided. In derivative of the angle. So they both will get cancelled. So I can write now this as 1 by 2 into minus 1 by 2 into cosec 2x into cot 2x plus integral of minus 3 times. So it becomes minus integral cosec 2x into cot square 2x. Remember, this problem is an I method. So I need to bring back to cosec cube 2x. So this cot square 2x will be replaced by this cosec 2x. Now cot square 2x I'm going to replace by cosec square 2x minus 1 into dx. So that became 1 by 2 into cosec 2x cot 2x minus integral cosec cube 2x. Remember, always when you bring back to I will be with a negative sign. Never I can be a positive sign. If I become positive sign, that means you have made some error. Plus, this when multiplied with this 1, you'll get a minus sign. Minus of minus will make it plus. So integral cosec 2x dx. So I can write I is equal to half into cosec 2x cot 2x minus I, right? Minus I. Then again plus cosec 2x integral will be plus, either you can write cosec 2x minus cot 2x upon 2, or you can write log of tan x by 2 plus c. C1 will put, because C1 is going to change. So 2i is equal to, I can take a 1 by 2 common. So cosec 2x cot 2x plus log of modulus tan x plus C1. I did not explain this integral of cosec 2x. Remember, what is integral of cosec? Integral of cosec x dx is log of tan x by 2. This is a formula for integral of cosec x. So naturally, integral of cosec 2x will be log of tan x by 2, coefficient of x. You have to divide by the coefficient of x. So finally, I is equal to 1 by 4 cosec 2x cot 2x plus log modulus tan x plus c, where c is c1 by 2. So that gives you the answer for the integral of cosec cube 2x. Now, next problem, I'm going to come to another I method problem. Change the color to black. Okay. Another I method problem. Integral e raised to, let's say, 2x into sine, let's say, 4x. Another problem with I method. Here we can apply integration by parts, our normal method. What was our LIATE? So exponential is last. So this has to be second function. And this got to be the first function. So first function, fis minus integral this. Fis minus integral dfis. So first into integral of second minus integral of derivative of first into integral of second all into dx. So you can write the answer as sine 4x into e raised to 2x into 2 divided by 2. Whereas derivative will become cos 4x into 4 into e raised to 2x by 2. Into dx. So this 4 and 2 can be cancelled. It will become 2. So I can now write this as (1 by 2) sine 4x into e raised to 2x minus 2 times integral cos 4x into e raised to 2x dx. Now again, I am going to apply once more integration by parts. So 2 times here you'll have to find integration by parts, whereas in the previous problem, we had to do only once. So 1 by 2 sine 4x into e raised to 2x, 1 minute. So now I can write this as e raised to 2x minus 2 into first function into integral of second minus integral of derivative of first into integral of second all into dx. So that became 1 by 2 sine 4x e raised to 2x minus 2 times cos 4x e raised to 2x by 2 minus derivative of cos is minus sine 4x into 4 into e raised to 2x by 2 dx. So I'm going to open this bracket. 1 by 2 sine 4x e raised to 2x. When you open this 2 and this 2 will get cancelled. Cos 4x into e raised to 2x. This will become 2, this 2 and this 2 will get cancelled. So become 2 into 2 becomes 4, and there is 3 minus sign, so 4i. Sine 4x into e raised to 2x is nothing but your I. So you are compared to I plus C1. Now this 4i and this I will get, always remember i's coefficient will be negative sign. So 5i is equal to, here what I can take common, e raised to 2x can be taken common. So e raised to 2x I'm taking common. Sine 4x divided by 2 minus cos 4x plus C1. So I can write final answer. This 2 if I take LCM, I is equal to e raised to 2x upon 10. I'm taking 2 as LCM, and that 2 is multiplied with this 5. That's how 10 it became. So sine 4x minus 2 cos 4x. And then this 5 has divided C1. So where C1 is, C is C1 by 5. So with that, we get this answer. That C is C1 by 5. So this is how you can integrate. So you can make a generalization in this particular problem. So I'm going to write the general formula for this. If you can remember, well and good. E raised to ax sine bx plus c dx. You will always notice that e raised to x will be the common factor, a square plus b square into. You will notice that there's a coefficient here with a sign, and there's a coefficient here. So you will be getting the answer as a sin x, a sin bx. So a sin bx plus c minus b cos bx plus c plus c. And when you integrate e raised to ax into cos bx plus c, your answer will be e raised to ax upon a square plus b square. This doesn't change. Now it will be a times cos bx plus c and plus b times sin bx plus c. This is your answer. So for example, in the previous problem, it was e raised to 2x into sine 4x plus c. 4x, not c, 4x. So your answer would be e raised to 2x divided by 2 square plus 4 square into a. A is how much here? A is the coefficient of 2 sine 4x minus b is 4 cos 4x plus c. You can notice that your answer is 20 here, but a 2 is taken common. So sine 4x minus 2 cos 4x plus c. This answer should tally with what we have got the answer before. Let's have a look at it. E raised to 2x upon 10 sine 4x minus 2 cos 4x. Have I got the same? Yes. So this is a formula which you can learn it. Very easy to remember. This part you have to remember, e raised to x is divided by a square plus b square. A times sine minus b times cos. Whereas here, a times cos plus b times sine. That's only one small sign difference that you have in the format of this two problems. So even if you want to derive this, the same method has to be applied. So as far as exam is concerned, you need to apply this method to get the answer. You cannot use the formula directly. For JEE question, you may apply this as a direct formula. Then now I come to the next kind of problem. Integral sine of 2 log x into dx. So sine bracket 2 log x. Usually this is bad angle problem where angle is put as t. You can also do that method, but you will put log x as t. So one method 1. I'm going to teach you two methods in this problem. Method 1. You put log x as t. Derivative is not present, so make x as a subject. Now differentiate. Dx equal to e raised to t dt. You know by definition of log x, x can be made subject. Base of the log will go to the base of the right hand side. So now if I replace this question, it will become integral sine 2t into e raised to t dt. So now this is same as the previous problem. You can see it is same as this format. This is one method of handling the problem. Second method of handling this problem is you can write this as I method. I'm going to do this also I method. I will write that sine of 2 log x into 1 dx. Now here 1 is easily integrable. So this is the first function and this is the second function. Always you know that whenever in one method, 1 is taken as a second function. So the first into integral of second minus integral of derivative of first into integral of second whole into dx. So this became sine of 2 log x, integral of 1 is x, minus integral of derivative of sine 2x, cos of 2 log x into derivative of 2 log x into integral of 1 whole into dx. Now what happens here? This x will get cancelled. So I can write this now integral as x sine of 2 log x minus 2 integral cos of 2 log x into 1 dx. Again, once more, I'll apply integration by parts so that I come back to sine. So again, this is first and the second. This time I'm going to integrate directly. X into sine of 2 log x minus 2, I put a bracket after this. First into integral of second, integral of 1 is x, minus integral of derivative of cos is minus sine 2 log x into derivative of 2 log x into integral of 1 whole into dx. So I'll cancel this again. Now, when I open this bracket, I will be getting, I can put integral constant C1 here because I completed the integration. So if I open the bracket, I will be getting x sine of 2 log x minus 2x cos of 2 log x. Now, when you open this bracket, 2 into 2 will become 4, minus, 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 and remaining is I plus C1. So it became 5i is equal to, remember left hand side is I. So when you add both 5i, this I plus this 4i will give you 5i is equal to, take x common like last time, sine of 2 log x minus 2 cos of 2 log x plus C1. When I divide by 5, it will become x by 5 into sine of 2 log x minus 2 cos of 2 log x plus C, where C is C1 by 5. These are the problems that is based on I method. Now after this, we have 3 formulae which is derived using the same method. Usually they ask this for examination. So let me teach you that formula. This is a theorem. Prove that integral root of x square plus a square dx is x by 2 into the question plus a square by 2 So first one is x by 2 into the question. Repeat the question as it is. Plus a square by 2. Now I just recap what is the integral of 1 by root x square plus a square. It's a standard formula. It is log of x plus denominator. This is a formula for this integral. So that you need to write here. Log of modulus x plus root of x square plus a square. So let's try to write the answer for, you need to by heart this formula. Suppose I'm integrating root of x square minus a square. What will be the change? X by 2 into the question minus a square by 2 into log of x plus root of x square minus a square. Most common question in the board exam. This is the most common question. They ask you to prove this theorem. Most of the time they will ask you this. Next, last one, root of a square minus x square. Same method, x by 2 into root of a square minus x square. Did you notice that here a square was negative, you got a minus sign here. Here a square is positive, so a square only, a square by 2. But what is the integral of 1 upon root a square minus x square? It is not log, it is sine inverse x by a. So naturally, here your answer will be sine inverse x by a. This formula is very useful. This formula is most of the time used in application of integration. We call it area under the curve. This three formulae we require it. And also we require this three formulae for the theorem proof. They ask in the exam this one of them. Every alternate years this particular problem theorem comes. So you need to learn them. Very easy to learn. No problem at all to learn it. So I start with, this is also I method and one method. So let I is equal to integral, let's say root of x square plus a square. So I will write as into 1 dx. Okay, I'll write the next step. Root of x square plus a square into 1 dx. This is very important step. Then you will apply integration by parts. Phys minus integral dphys. First one as it is. Integral of second minus integral of derivative first, integral of second, whole into dx. So you will be writing this as root of x square plus a square into x minus, now derivative of root x square plus a square, derivative of root u is 1 by 2 root u into derivative of u. So I need to apply that formula over here. So I can say like this, I need to apply this formula here. So derivative root 1 by 2 root x square plus a square into derivative of u, derivative of x square plus a square into 2x. Integral of 1 x dx. Now again this 2 will get cancelled. Now I will write this as x root of x square plus a square minus x square upon root of x square plus a square. Now what should I do? Denominator is x square plus a square. So what I am going to do after this is, I will add an a square and subtract an a square. This is an important step. Add one a square, subtract an a square. Why? So that the denominator, there is a cancellation possible. This step is a very important step. So when I separate the denominator, when I separate this denominator, it becomes x square plus a square divided by root of x square plus a square dx. Minus of minus, this become plus a square integral 1 by root x square plus a square dx. I took a step little differently. This upon this give me first term. This upon this gave me the second term, but constant I wrote it outside. Minus of minus made it plus. Now I can cancel this both. When I cancel, what is a by root a? You know that it is root a into root a. So one root a will get cancelled. Same way, x square plus a square upon root x square plus a square will become x root of x square plus a square minus root of x square plus a square with the integral sign. Plus, this is a direct formula, a square log of modulus x plus root of x square plus a square plus c1. Again, like last time, the c1 is going to change. Now this is nothing but I, the same as the question. You can see the same thing over here. So I can replace this by I. So my next step, I don't have space to write here, so I'll just put a line here. So I is equal to x root of x square plus a square minus I. So this I have denoted by I because it's the same as the question, plus a square log of modulus x plus root of x square plus a square plus c1. I don't have space properly, so there is congestion there. 2I is equal to x root of x square plus a square plus a square log x plus root of x square plus a square plus c1. Now when you divide by 2, this becomes x by 2 root of x square plus a square, and this will become a square by 2 log of x plus root of x square plus a square plus c, where c is c1 by 2. Very, very important. This particular theorem proof you have to learn. I'll give one more practice, one more theorem, but next one you try to do it yourself and then check whether what you have calculated is correct or wrong. So let me take one with a minus sign, that is one which has got negative sign. This I'm not going to do. This I'm going to do because there's a minus sign. So that can be little complication while you do yourself. So let me teach you that now. So now I'm going to start with the second theorem. I is equal to integral root of x square minus a square into dx. So this I'm going to write as root of x square minus a square into 1 dx. If I'm in shorter space, I'll write it over here. So I'm starting here. So this is, which is first function? This is first, this second. So first into integral of 1 dx minus integral of derivative first Now I can write this as directly the answer, x square minus a square into x minus derivative of this 1 by 2 root x square minus a square into 2x into integral of 1 x dx. This 2 and this 2 got cancelled. So this became x root of x square minus a square minus, here I will get x square, okay, upon root of x square minus a square. Now to bring the denominator term in numerator, I will add an a square and subtract an a square. So subtract an a square, then add an a square. Then only they will match, then only cancellation is possible. So I will write this as x root of x square minus a square minus, I'll separate it, x square minus a square upon root of x square minus a square plus a square upon root of x square minus a square. Last time I didn't have enough space, so this step I just did it directly. Now when you open the bracket, this will become negative. That's why minus sign comes. So x root of x square minus a square minus integral. This cancellation will give you root of x square minus a square dx. This minus of plus will give you minus a square outside integral 1 upon root x square minus a square. So finally, I'll get my answer like this. Okay, I think that will be enough. So I is equal to, let me use some other color. I is equal to x root of x square minus a square minus I minus a square. Integral of this is standard formula, log of x plus root of x square minus a square plus c1. So 2i is equal to, finally, 2i is equal to x root of x square minus a square minus a square log of x plus root of x square minus a square plus c1. So I is equal to x by 2 root of x square minus a square minus a square by 2 log of modulus x plus root of x square minus a square plus c, where c is equal to c1 by 2. So that's how we can calculate this. So this proof is also very important. So don't neglect studying this. This proof is quite common in the exam, and probably you may be having this in the exam.